So today let's talk about circular motion, rotational motion, essentially an object going around in a circle. So when we have a circle like this and an object goes around it, we have to consider that motion a little bit differently than we consider the motion of an object in a straight line. So this is just going to kind of be a review of the things you need to consider that are rotational and how they kind of relate to the translational or linear motion of an object. So I drew in a radius here for an object, and radially out here on the edge, this is where our object travels in that circle right here on the edge. And we don't use normal x and y coordinates. Rather, we use a radial and tangential component to describe at any given moment where that object is located in space. That radial component, this is the radial part, we refer to as the Greek letter rho. The tangential component is the phi vector. Now it's important to note that just like in translational mechanics, in rotational mechanics you deal with ideas of like displacement and velocity and acceleration, except it's a little bit different for linear versus translational, or rotational, excuse me. So in the linear world, we have things like, R for position, or X, Y, Z. In the rotational realm, we think about things in terms of theta. We are worried about how much of a rotation it's done. Has it done 2 pi, which is one full rotation? Has it done 4 pi? Has it done pi, which is only half a rotation? We are more concerned with the number of rotations than we are how far did this object travel, because ultimately we don't really care how far it traveled in terms of rotation. We just want to know where is it on the edge of the circle, and theta tells us that. Likewise, linearly we have velocity, and rotationally we have angular velocity, and that's not a very good omega, so let me redraw that there. And then again, we have a linear acceleration, and we actually have 2 linear accelerations we need to consider. One of them is in the radial direction, and one of them is in the tangential direction. So we have a rho, which is the radial acceleration, also known as the centripetal acceleration, so you'll sometimes see it written as acentripetal. And then you have this tangential acceleration as well that functions in the tangential direction. And there is also, of course, a rotational acceleration or angular acceleration. So you can kind of see how these pieces line up and, they're counterparts, so to speak. But what we haven't talked about is how they relate to one another. So let's look at that. One is how they compare. I'll just draw a line right here. Your position r is related to the radius r times theta. So that should make sense to you, because if you go around a circle at the distance to the radius, you've outlined the circumference. It's 2 pi r. That's the distance you traveled. So hopefully you can keep that in mind. V, likewise, is related to r omega. And then here, the tangential acceleration is equal to r alpha. However, your centripetal acceleration points inward, so it gets a negative sign. Omega squared r. And let me remove that. That is not a good place to put that. Let's just get rid of all that. and put it somewhere more useful because you can't see that. Go away. Let's try that again. So that a centripetal piece is actually going to be equal to negative omega squared r. So those are our relationships there. I don't really like how that turned out. Let me see if I can recopy that. Apparently it's decided on its own to have a weird color for red from now on. So those are those relationships, and I just want to make sure that they're straightforward and present for you to understand. We're going to look at an example that relates these very basic, not using calculus, but I'll talk about calculus in how it could be used. We're just going to do a linear example in the next video. So tune in for part 2, which will be coming shortly. Okay then, this is part 2. So everything should be clear on your screen, and we're starting back over, and we're going to talk about an object, and we're going to let it, simplest thing is spin up. So at event 1, we're looking at an object at rest. And then maybe event 2, we can call that top speed. So we're going to be looking at that. And in that, we have time as always a variable. And we have positions, which up until now haven't been something we refer to beyond like the radius. So we'll have a radius and we'll have theta. I'm not going to worry about the position function. And we'll have the radius at the end and theta at the end. Notice the radius is going to remain the same. Then we also have to consider our velocities, angular and linear. And then the last bit is the accelerations, where we have, a radial or centripetal, and then a tangential, and then alpha. So lots of acceleration. There we go. So we just have this thing going from rest, which tells us a whole bunch of things. For example, it tells us that we can start at 0 seconds. We can have a fixed radius. I'm going to give it a fixed radius of 3 meters. It's gone 0 radians around. That radius is going to stay 3 meters. I'm going to be nice and say it reaches its top speed in 10 seconds. I'm being nice to myself there. Its initial speed is 0 meters per second. Its initial angular speed is 0 radians per second. And because, if you recall, in the first part of this video, because this is based on this, then this is also 0 meters per second squared. And we're actually going to have the tangential and alpha. We're gonna have a value for that because it's going to be constant. All right. So in this example, I would be saying, to put it in calculus terms, essentially v or omega, either one. They are a linear function, which means that alpha, or A. A tangential, or alpha, is a constant function. And I'm going to make this simple and just give us that constant function, mainly because I'm trying to keep the example simple, and we can talk about the more complex stuff. This is just as a reference. So I'm going to say that alpha 1 is 0.5 radians per second squared. Now, if that is true, you can refer back to the earlier relationship between A and alpha, and you know that A is equal to R times alpha, so it's going to be 3 times that, or 1.5 meters per second squared. And because that's a constant function, it's not going to change in the next little bit of time. So this will stay 1.5 meters per second squared, and this will stay 0.5. However, this value is going to change, this value is going to change, this value is going to change, and this value is going to change. We could do this the calculus way or the kinematic way. For example, in the calculus way, we can determine what this coefficient is. It was given to us, alpha equals 1/2. Therefore, our coefficient A is 1/2. And that would translate into omega of t would be 1/2 t. The velocity then function would be r times omega of t, which would look like 3/2 t. So we can do it either way. I think we're going to do it with the calculus way because I've kind of already started it. You could use a kinematic model because this is a constant acceleration, but we're just going to use this calculus one. So this is nice because now we know that v of 2 is actually, or v sub 2 is v at 10 seconds there. So that's going to be 3/2 of 10, or 15. So we know that this is 15 meters per second. And if we divide that by r, we can find omega, because remember, omega is v over r. We know that if you divide that by 3, you get 5 radians per second. And then the next piece then is dealing with a centripetal, in which we know that it is negative omega squared r. So we're looking at 25 times 3, so that's negative 75 meters per second squared, which is pretty intense. That's like 7.5 Gs. You would not be a happy camper at that point if you were experiencing that type of centripetal motion. Like if you were on a carnival ride, it would be like a carnival ride of doom. So avoid it at all costs. And then the last thing to look at then is just our little how far we went. And you would do that by integrating, right? Theta of t would be, that was not a very good t, would be equal to the integral of omega of t at this point. So if you integrate that and you understand that you're going to be at 0 radians, so your initial at the beginning, so your initial constant's going to be 0, you're going to end up with theta of t is equal to, and remember what you're integrating is v divided by r. So what you're going to be integrating is 1/2 t. So you end up with 1/4 t t squared. So, and if t is 10, then that's going to be 100 divided by 4, or 25 radians, which is, if you divide that by 3, it's roughly like 8 rotations, if you want to keep track. So that is a simple example, and we did use a little calculus, but we kept it grounded in something you could do mechanically with kinematics. But that's pretty much it, covering all our bases in linear and angular for velocity and accelerations. So until next time, stay physicsy.